All right, so welcome to the last lecture of the semester. We do have three more lectures scheduled, but those are going to be devoted to final projects. So Wednesday, next week Monday, and next week Wednesday will all be final projects. I did post the schedule for that already on Piazza. Um, there are a couple of people, a small number, maybe two or three people on that schedule who still have not submitted their final project proposal, and I've emailed them several times and I've never gotten a response. So I'm not sure if those people are actually just not in the class and maybe forgot to drop it. I'm not really I don't know, but I guess we're gonna find out Wednesday, or um, I'm gonna send them a final ping right after this lecture, and if they don't respond before Wednesday, then we'll just remove them from the schedule and assume that they're not actually in the class anymore. I'm also going to have, I didn't have office hours this past Friday because it was the Thanksgiving holiday weekend. I will have it this Friday, but some of you are presenting on Wednesday, so office hours on Friday are not that helpful. Um, so for anyone who, maybe I'll make a Piazza post, but basically, if there's anyone for whom it would help to have a meeting before they present on Wednesday, I'm happy to open up some office hours tomorrow on Tuesday. Um, so just let me know. So we've talked a lot about various things in this semester so far, right? We've started off with basic streaming problems, counting problems in the streaming model. We talked about lower bounds. We talked about linear sketching, uh, de-randomization, dimensionality reduction, randomized linear algebra, and compressed sensing. And then we talked a little bit about um, kind of instance-wise bounds using kind of the theory of stochastic processes and the sparse Fourier transform. So today, I just want to end with kind of one more topic. Again, this is just one lecture, so we're not going to get too deeply into it, but it is something that I think is a useful thing that I should definitely at least tell you about, you should know about. Okay, so today, we're going to talk about core sets. And I'll just say, see more in the survey. It's a brief survey, but it's a gateway survey, so it has links to lots of other things that you can read. It's not very comprehensive. See more in the survey by Bacham, Lucic, and Kraus. So, what is a core set? Um, so, there are both what are called weak core sets and strong core sets. Okay. Um, but what unifies them is basically a weighted subset of the input data such that optimizing over the subset gives a near optimal solution for the original data. So specifically, this is what's called the weak core set. A strong means the cost of any solution to the subset is approximately the same as to the original. Maybe I'll try to make this concrete, but basically what this is saying is, let's say that you're trying to solve k-means, right? So k-means, you have a bunch of points. And I'll make this more formal soon, but okay. So let's say you would like to cluster these. I mean, this has a very obvious clustering, but let's say that you'd like to cluster this into 4 clusters. You know, the optimal clusters are something like, you know, maybe choose this point, this center, this center, and this center. Okay. These red points are the opt centers. The black points are the original points. Okay, what is a core set? A core set is, for example, so let's say this orange is the core set. So what does it mean that it's a core set? Well, if it's a weak core set, what it means is suppose that you forget about the black points altogether. Okay, the only the only information you retain is the yellow points. Okay, and now I ask you to optimally or almost optimally cluster the yellow points. You're probably going to come up with a clustering with 4 cluster centers that are pretty close to those red centers, which are the optimal centers, right? So that's what it means to be a weak core set. It means that if you optimize, a subset is a core set. I'm going to write it more formally, but a subset basically is a core set, and it could be a weighted subset. So, for example, this point right here, we could give it, the original black points all were 1 point each, so they all had weight 1. But we could make the yellow points weighted. So, like, for example, this point maybe has weight 3 or something. Okay, but the point is, if you then, and when I say weighted, I just mean like you imagine that there are 3 copies of that yellow point, but we don't have to remember all 3 copies. We'll just in memory, to minimize our memory, we'll just remember the number 3, that there are 3 copies of that point. But in terms of evaluating the cost function for k-means, we're going to act as if there had been 3 points there. So the distance squared from that yellow point to the center will get multiplied by 3 because we imagine that there are actually 3 points there. Okay, so what it means to be a weak core set is if we forget about the black points and we just give someone the yellow points and we say optimally cluster these yellow points or optimally find centers or near optimally find centers for these yellow points, whatever cluster centers you find will be nearly optimal for the original black points. Okay, so we basically reduced to the optimization problem over a smaller set. Okay, that's what it means to be a weak core set. To be a strong core set means not only is it true that optimizing the yellow points gives a near optimal solution for the black points, but even crappy solutions to the yellow points have their costs approximately preserved. So you can imagine, like, take those yellow points and look at the following, 4 cluster centers. I'll put like 2 over here, 1 here, and 1 here. Okay? So those 4 points that is a valid, choice of 4 centers. It has some cost for the yellow points. Not a great cost, not nearly optimal, but it has some cost. To be a strong core set means whatever its cost is for those whatever the cost of those teal points is for the yellow points, its cost for the black points would be almost the same, up to a constant factor, or up to 1 plus epsilon, or whatever the quality of your core set is. So that having that level of preservation is what it means to be a strong core set. Okay? So does that make sense? The difference between this is definitional. What's the difference between a strong core set and a weak core set?
Yeah.
Okay. So I just want to, in this lecture, give you a couple examples of how do you construct core sets. And then I want to say that having core sets gives a pretty generic way of designing streaming algorithms, low memory streaming algorithms for optimization problems. Okay. And actually, maybe what I'll do is I'll first say that. So the claim, again, I'm going to write it informally, and then it's going to be clear from the calculations what we're getting mathematically. But the claim is that there's a systematic way. This is an informal claim. There's a systematic way of turning a core set construction, right? The name of the game in core sets is obviously you want to make that subset, that yellow set, as small as possible, because presumably it's harder to optimize over a large set than a small set. So if I can turn my large data into small data by taking a subset, a weighted subset, I can optimize over that probably more efficiently. Right? So if there's a systematic way of turning a core, so the claim is that there's a systematic way of turning a core set construction into a low memory streaming algorithm for that optimization problem. Okay, and the proof, again, there's no real proof here because I'm not saying anything mathematical. You can write down, so you can formalize this, but I think it's going to be obvious from what I'm writing that what I mean here. The basic idea is that the core set of, let's say, I'll say it as the core set of a core set is a core set. Okay, so let's, for example, take, k-means. So we see a stream of points in k-means. This is some point in some metric space. This is some other point in the same metric space, etc. Let me just draw a few more circles. Conceptually, this is what I want to do. Okay, I'm going to imagine that there's actually a perfect binary tree built on these endpoints. So I'm seeing endpoints in a stream, or coming at me in a stream. Right? And I don't want to have to store all of them. Okay. So what I'm going to do is I'm going to, so let's say my memory is going to look like this. So first I'm going to see the first point, and then I'm going to store it. Then I'm going to see the second point, and then I'm going to store it. Okay. And then what I can do is I can then, merge these two into a core set. So, I mean, let's say that our cost, what is our cost, right? Is basically the sum over all x in the point set. Well, okay, so yeah, let me do it like this. The distance from x to the centers, where C is a set of k centers, and actually it's the square distance. Okay. And for this, what you actually want is you want a core set, you want a core set that basically has the property that if you add more points to the core set, then it still remains a core set, right? So I guess what I'm saying is you want the property that if you look at the cost, like for all possibly weighted subsets S of the point set, if you look at the cost function on S, and for all, let's say, T, which are possible extensions, to X, points that you might add later, the cost of S union T applied to some solution, C is the solution, it's the set of centers you're using, let's say, is at most the cost of X union T C, and which is at most, let's say, some alpha, or beta, which is the approximation factor times the cost of S union T C. Okay. So you want a core set construction that has this property that, if you have your core set and you extend it by an arbitrary set, which is like the set that you're extending your points by, then you still have this cost maintenance property. So this would be like this, as I wrote it here, would be also kind of a strong core set property because this is true for any T. Or true for any C. Okay. So what you would do is you would basically, you would store this as like that point as a core set of itself. Of course, the set itself is always a core set of itself with approximation ratio 1. Then you see the next point, you would see this and store that as well. And then you would stop storing these, and then you would run your core set construction procedure on these 2 points, and then you would get a core set that you store, which is the core set of those 2 points. Then you see the next point, you store it. You see the next point, you store it. And then you're like, I'm actually going to now merge these. And then I'll merge them into a core set of that data. And then now I'll take these two weighted subsets of different sets of points and merge them. And then I'll take a core set of the union of these two. So a core set of the union of these two will give me a core set up here. And then now I don't need to store these anymore. And you just kind of proceed in this fashion. And the point is, you'll always have at most log n active nodes in the tree where you're actually storing any core set at all. So that means that this construction implies that if the original core set construction gives size s, then the streaming algorithm uses space of s log n, and the approximation factor, the quality of the core set, becomes something like beta to the log nth power, right? Because if you lose a factor of beta every time you create a core set, like every time you take a data set and create a core set out of it, you lose a factor of beta. If you do this log n times up the tree, you're losing beta to the log nth power. But what you'd want then is we'd want something like beta to be something like 1 plus epsilon over log n. That would imply that beta to the log n is equal to 1 plus O of epsilon. So if you have a way of, for example, for k-means or k-median, constructing a small core set, and it turns out that this is possible, a core set of size something like poly k, poly log n, poly 1 over epsilon. If you have a way of doing that, then you automatically, and it has this property also that I mentioned here. Oops. And it has this property, then you automatically have a low space streaming algorithm. Okay. So it's useful in streaming, but honestly, people even outside of streaming care about core sets because it's just a nice way of summarizing data into a lower memory form. Okay. So let me give 2 examples for today. One is going to be k-median. So k-median is min over the choice of C should be like, let's say, so we're given data set X. In some metric space with distance function, let's call it D. We want to find the argmin over all C, which are centers, a subset of X, the size of C is K, of the sum over all points P in X of the distance from P to C, where the distance from P to a set, the distance from P to a set is just defined to be the min over all centers in that set of centers of the distance from P to little c. Okay. So it's very similar to k-means. K-means is the square version. It's where you take d squared instead of d, and usually, I mean, not always, but oftentimes people study the case where d is Euclidean distance. But you can study these problems in arbitrary metrics.
So this looks like it's just k-means for the L1 norm, or is this actually a median that's getting computed?
D could be the Euclidean distance. So, right?
Oh.
So, like D isn't, so I'm just, so K, if I said k-means, I think when we talked about k-means earlier in the class, D was Euclidean distance, but more generally, sometimes when people say k-means, what they actually mean is this.
Okay.
So median just means you take the sum of distances to the centers. Means you take the sum of distance squared. But as we talked about k-means earlier in the class, we focused on Euclidean distance, which I think is probably the most common one that people talk about.
Well, I'm getting tripped up by the word median. Is there actually like a median getting computed here?
Yeah, so this is just, I guess, the standard terminology in the literature. Why is it called median? I think if you take the points to be one dimension, like numbers, and you take the distance to just be the absolute value of the difference, then and you look at the case where k is 1, then the optimal center is the median.
Okay.
Does that make sense?
Yeah, that makes sense.
So kind of k median is a generalization where you don't just want one center, but you want k. And then people in the literature tend to further generalize it where it's an arbitrary metric space and not just absolute value of difference on a line.
Okay.
Yeah. Thanks. Again, this is just the jargon of the field. This is what people call it. Okay. Yeah. So again, we're not dealing with the means version. But people construct core sets for k-means as well, and they get very similar results. The other one that we'll look at is minimum enclosing ball. Which is also, it goes MEB, which is compute the argmin. So again, you're given, let me write it again, you're given set x, and here x has size n. You're given set x as above, it's size n, actually we're going to look at the Euclidean space. Okay, so you're given a subset of Euclidean space of size n, d-dimensional Euclidean space, and you want to find the smallest radius ball that encloses all the points. So find the min over all the argmin, I guess, over all origins, centers O in RD of the max over points in X of P minus O. Right? So you have these points. You could choose this center, which would probably be a terrible choice, because if you want that to be the center of your ball, probably the ball has to have radius that looks like this. That's not a very perfect ball. It's very lopsided, but you get the idea. A better choice would have been something that's kind of smack in the middle. And then probably the smallest ball is this ball. Okay, that doesn't quite contain everything, but let's pretend that it does. Let's delete the point that's not in the ball. Okay, delete the 2 points that are not in the ball. Okay, so that this yellow one would be the optimal one. Okay, does that make sense? The problem statements. So I want to talk about kind of optimal, or not optimal. There's some constructions that are known for these problems. It turns out that, sorry, just give me a second. Just want to make sure I say the correct year. I think it's Feldman and Langerman and Langberg. So for like something like k-median, for example, Feldman and Langberg in 2011 showed that core sets of size, something like K O of kd over epsilon squared exist and can be efficiently constructed. Right, so it's pretty nice. I mean, it's and the quality is beta, which is 1 plus epsilon. Right, so this is specifically the case of, I think this is the case of d-dimensional Euclidean space. So capital D is d-dimensional Euclidean. But people have also worked on kind of more general constructions that work in other metrics as well. Like, for example, the one I'm going to show you today is not going to do nearly as well as this, but it's going to get something that's non-trivially better than trivial. It's going to be non-trivially sublinear and works for arbitrary metrics. So let's see k-median. So today we'll get a weak core set of size O of square root of nk. Okay. So it's never worse than n, right? But if k is small, if k is a constant, you get a core set of size root n. And it can be iterated to get an arbitrarily small exponent. On n. Okay. At the cost of increasing the quality, or worsening the quality of the approximation. This is not going to be a core set that gets 1 plus epsilon. This is going to be a core set that gets some constant quality of approximation, big O of 1. Okay. So the assumption, I should give the reference for this. This was due to Guha Mishra Motwani and O'Callaghan. I want to say it was like maybe 2001. It's one of the earliest constructions. Maybe it's 04, but yeah, it's in the early 2000s anyway. I'll put the exact reference in the lecture notes. And the assumption is that there exists an offline O of 1 optimal approximation algorithm for k-median that runs in linear space. It just needs to, in other words, it just needs to remember O and D, O of let's say n points. With maybe O of n extra data. And it turns out that this has existed for at least 20 years. People have, I think the best known approximation ratio now that people can achieve is arbitrarily close to, like, today can achieve arbitrarily close to kind of 1 plus 2 over e approximation efficiently. But it does, the constant doesn't really matter for us. Let's just give this a name. This is b. So there exists some b approximation. I mean, k-median, by the way, and k-means are NP-hard problems. So that's why we're talking about approximation algorithms here. So our assumption here is just that there's an approximation algorithm that runs in, that's fast and runs in linear space in the number of points. And this is due to Cohen, Adad, and others. And it's somewhat recent. But even as far back as 2000, I think there was an algorithm that was arbitrarily close to a 3 approximation. So people have been getting better B's, but it's just from one constant to a better constant. And I'm not going to talk about how these approximation algorithms work. They're not really about streaming. They're just about designing approximation algorithms. So let's just take it as a black box that it exists. Okay, so the algorithm is, so we have this set of n elements. We're going to break it up into B blocks, or blocks of size B. Break into n over B blocks of size B. So each one has size B. And then what we're going to do is we're going to run a B approximation in each block. Okay. And that's going to give us I guess k points per block. Oops. So bk points total. No, not bk points total. N over b times k points total. Right? When we run the B approximation in a block, it's going to spit out, like when I say run the approximation in each block, what I really mean is pretend the blocks have nothing to do with each other. Each block is its own k-median problem. And I just want to say, like, find the best clustering for the points in this block, ignoring everything else. So you're going to spit out k points, which are your best centers. And here you're going to spit out k points, etc. Right? And since the number of blocks is n over b, the total number of points here is n over b times k. Okay? And this will be our core set. What's the space requirement? So the space is in each block of size b, wait a second. So, yeah. So in each block of size b, we're using a linear space algorithm. So we're using b space per block. And we also have to remember all the cluster centers that we're finding along the way until the very end. So we also have to remember n over b times k points. So we minimize this expression by setting the two terms equal. Minimized when b is equal to n over b times k, which implies that b squared equals equal to nk, which implies that b is equal to the square root of nk. So this implies that the total space then becomes O of square root of nk. And also the core set size becomes O of square root of nk. So we're able to construct a small core set in low memory. Right? I mean, maybe I should, yeah, so maybe I should have said this in the beginning. For the purposes of constructing weak core sets, the name of the game is always to compute the weak core set using low computational resources, right? Like low memory, low time, whatever. Because if you didn't care at all about, let's say for k-median, if I said, look, I want you to get me a really good core set that's really small, really good approximation ratio, like what could you do? If you didn't care about computational resources, what would be like an amazing weak core set? Well, just the optimal solution itself, right? So, right, if you take the optimal solution and then you know that's k points, and then you try to find the best k clustering of those k points. That's going to be the points themselves, which is an amazing solution to the original point set. So, if you're allowed arbitrary computational resources, then yeah, just use the opt itself as the core set, and that is a weak core set. But that's kind of uninteresting because this is an NP hard problem. It's not easy to come up with the optimal points, right? So the name of the game really is like how good can you make, how small can you make your core set, or how good can you do that, how well can you do this when you have some constraints, like for example here a space constraint. So here in sublinear memory, we're able to actually compress into a sublinear size core set. Okay. And now what I want to show you is if you take this core set of root nk points and you optimally or near optimally cluster it using k centers. Okay. So now this is your new set of points. I want you to k cluster that set of points. I claim that the clustering you find will be approximately optimal for the original data set. It'll also be O of 1 optimal, where the O of 1 will be something like b squared. It'll be roughly 4 times b squared. Okay. So we'll show that this core set has approximation quality at most 4b times b plus 1. So roughly 4 times b squared. So the first claim, yeah, so first before claims, let me just write some notation down. I'm going to say that cost of AA, or let's say cost of AB, is the best k-median cost possible to cluster A when the cluster centers have to be in B. Okay. So the first claim is that for all A and B, the cost of clustering A with centers in A is at most 2 times the cost of clustering A with the centers in B. Okay. Why is that? So let's say we have A. So this is A, and this is B. So we have our point set. And let's say I'm doing k equals 3. Maybe what I do is I say, look, I'm going to choose this as one center. These are the optimal centers. These 3 are my optimal centers. So I'm clustering A using centers that also themselves are in A. Now, what's B? B is some other set of points. Like maybe B is all of space, for example. Let's say B is all of space. What would the optimal centers be? Probably something like this, roughly this. For k means anyway, it'd be this, right? Which would be the centroids. And the point is that if you look at the distance from any one of these points, if you look at the distance, let's say, so what is k-median? K-median is like the sum over all points in A of the distance from the point set to its closest center. So for example, that would be like the sum of these distances. Like for example, this distance, etc. And then the distance to itself there. Let's look at any one of these terms. Like let's just give these names. Let's say that this is little c for center and this is a point little p. Then on the one hand, on the left-hand side, we have the distance. And let's say this orange point is q. The distance from P to C is at most the distance from P to Q plus the distance from C to Q. This is just triangle inequality. Right? You see, and then what I want to say is okay, sorry, I think I confused myself, but I think what you want to do is basically now sum over all points P. Yeah, this is definitely. Sorry, I think I might have to fix this in the notes. I think I confused myself in my own notes, but this definitely part here would be the cost. This would be the cost of AB. And this would be the cost of AA. And then I guess I would somehow have to argue about the sum of this part, which for some reason is eluding me right now, but let me fix that later. Let me not try to unconfuse myself live because I'll probably just eat up some time. But I'm pretty sure that that I can come back and fix this inequality. Okay. And now let me go back and name these subsets. So remember, the whole thing originally was X. Let me call this subset X1, X2, and this is X n over B. And now what I want to do is I want to look at claim 2, which is just that the sum over all I of the cost of xi using centers in xi is at most twice the cost of clustering x using centers in x. So the proof of this is just via the previous claim. So what I can say is the sum over I of the cost of clustering xi using xi is at most twice times the cost of the sum of the costs of clustering xi with C, where C is like the actual optimal centers. And this is just 2 times the cost of clustering X with the optimal centers. Okay. Okay.
Wait, did you mean to write something different on the top line then?
Oh, yeah, probably I meant to write this. Okay. Okay, so now let me also look at, let's call this set of points let's call this x prime. which is the core set. So the size of x prime is O of root nk. Okay. Right. Very good. So I guess the first thing I want to say then is, if we B approximate in each xi, then we paid total cost at most the sum B times the sum over I of the cost of xi, which is at most basically 2B times opt, where this is for the original data set by claim 2. And then now I want to talk about what happens when we then try to optimally cluster x prime. Okay. And then we're going to add those two costs together. Okay. And by the way, I mean, x prime might be a multiset. It might be the case that some of these k points across sets are the same, but that's okay. Then we'll just treat it as a multiset or a weighted set. Okay. So we're just going to we'll use triangle inequality. So again, we have this, let's look at some q, which is in x prime, and consider the p's that are assigned so maybe I should say it like this. Q is in x prime, so I can say that it came from some xi. And what I say is consider the p's in xi that are closest to q, right? Because the things that are in x prime are like nearly optimal centers, cluster centers for the points in their partitions. So for any point in some x prime, it is the center that some of the p's in that xi are closest to. And then also consider the centers C closest to these p's. Okay. So what do we know? We know that the sum of costs, from the q's to the p's, across all the q's and p's, is at most 2b times opt. And also the sum of the costs from p's to c's to their respective centers is just equal to opt by definition. So therefore, what do we have? We have that the cost of, let's say, x prime, clustering x prime with the optimal centers is at most 2b plus 2b times the opt plus opt by triangle inequality, summing these two things, which implies that the cost of x prime using centers in x prime is at most 2 times 2 times opt. Well, 2 times basically this. So let me factor out an opt. 2 times opt times 2b plus 1. Okay. And then there was also what we lost by moving. There's also what we lost by moving from the original points to x prime. We lost this 2b opt. So then b approximation to x prime has total cost at most 2b opt plus actually yeah, plus did I write this correctly? 2 times 2b opt plus opt. 2 times 2b opt plus opt. So the total cost is at most 2b opt plus, or let me write it like this. Yeah, 2b opt plus this thing, which is equal to opt times 2b plus 2b plus 1. And this thing in here is what? 2b plus 4b is 6b plus 1. I seem to be bad at math because I was supposed to get 4. I know. So the point is, yeah, good. So the point is, if you optimally k cluster x prime, you'll get a cost of this. But we're not optimally clustering k x prime. We're getting a b approximation, right? All we have in our hands is an efficient b approximation. So actually, what I should have written is that our total cost is going to be 2b opt plus b times the thing above plus b times the thing above. And that's equal to opt times 2b plus 2b plus 1. And then I can factor out the 2b, and this is equal to 2b times opt times 1 plus 2b plus 1. And that's just 2b plus 2, so I can factor out a 2. And this is equal to 4b, b plus 1 times opt. Okay, good. So that's good. That's it. Okay. So that's of course not even close to optimal. The size of this core set is, it still has this dependence on root n, which is quite large compared to the best known ones we have, which are only like poly k. I mentioned the Feldman-Langberg one, which is kd over epsilon squared for d-dimensional Euclidean space, but even for arbitrary metric spaces, people can come up with core sets that have size like poly k. Like it shouldn't depend polynomially on n. And then the next thing I want to show you is minimum enclosing ball. And here we're going to construct a core set using something that you've already seen before, which is basically nets. We'll construct a core set of size O of 1 over epsilon to the d minus 1 over 2 using a net argument. So the nice thing here is it's totally independent of n, right? Of course, it has this very bad dependence on the dimension, but for low dimensional points, it's not bad, right? And it's completely independent of n. So what's the idea? We're going to take an alpha net of our point set P1 up to Pn. Call this alpha net, let's call it V, which is little v1 up to little vt, which is some subset of Rd. These are all in Rd. And we're looking at, remember, this is Euclidean ball. This is minimum enclosing ball under Euclidean distance. So the ball is measured as a Euclidean ball. And what do I mean by an alpha net? I want an alpha net in terms of angle. Oh, and actually I should say, I'm going to take an alpha net of the entire sphere. And the input is the point set P1 up to Pn. So what do I mean by an alpha net of the entire sphere? It's going to be an alpha net in terms of angle, as I mentioned. Meaning, for all x on the sphere, on the d-dimensional sphere, there exists a v in the net such that if you look at the angle between x and v, the angle between them is at most alpha. So for example, imagine we're working over two-dimensional space. Since we're only talking about angles, we can just think, we can even think everything here is on the sphere. The v's are on the sphere, the x's are on the sphere, because all that matters are angles. So there's my circle in 2D. So I said two-dimensional is the example. Kind of what's the best alpha net? The best alpha net is you just go around the circle kind of every alpha degrees. Right, where so, this is the origin. This is alpha. This angle here is also alpha, etc. Then, no matter what other point you take on the sphere, it's in between 2 points. It's in between 2 black points that have angle alpha between them. So its angle with either of them is also at most alpha. So in terms of angle, this is an alpha net. Does that make sense? And this has size, well, the circumference of a sphere, or the circumference of a two-dimensional circle is O of 1, right? It's, I guess, 2 pi. So the size of this net is like something like roughly 2 pi over alpha. It's O of 1 over alpha. So this has size O of 1 over alpha. And in general, you can get size O of 1 over alpha to the d minus 1, where d is the dimension. Okay. And, how would you argue that? It's very similar to how we argued about net sizes in the past. Basically, it's this relationship between covering and packing. So what you do is you basically, you look at this. Let's try and draw. Let's look at draw a 3D sphere. Okay, I'm very bad at drawing, by the way, but let's try. You basically greedily pack vectors. So you just take an arbitrary vector on the sphere. And okay, maybe that I'm really, okay, so again, this is not, I don't know how to draw 3D that well, but let's pretend that it's coming at us. So, you know, this right here is like the surface of the sphere. Okay. And then you ask yourself kind of like, there's some kind of patch on the surface of the sphere. Let's say this is the patch. Such that any of the vectors there are with an angle. Of course, the patch should look more, the patch actually is itself circular. I don't know why I drew this funny shape. There's some patch on the sphere around that point, which is basically all the other vectors that have angle at most alpha with this point, right? So I can greedily try to pack as many of these patches on the sphere as I can such that they don't overlap. Okay, so I'll pack circles on the surface of the sphere with radius something like alpha over 2 maximally, then double them, double the circle sizes to get a cover. So that gives me a cover, which is an alpha cover. And then the question, the reason it's a cover is because of triangle inequality. This is very similar to our greedy construction of nets in the past. The question then is just how big is this net? And it's just a calculation. Basically, you calculate the surface area of the d-dimensional sphere, and then you're saying, well, I'm packing all these little patches on the surface that are disjoint. So there's a volume ratio that kind of constrains how many possible disjoint circles I can have. Therefore, my bound on my net size is that volume ratio. Okay, so that's exactly the same volumetric argument we've seen in the past for bounding net sizes. And if you do that, you're going to get something like this. You're going to get a net size, which is O of 1 over alpha to the d minus 1, just by volume ratio. Okay. And then now okay, so good. So now we have this net, and we know how to construct the net via this greedy packing argument. Now, how do we get a core set? Okay. So to get a core set, what we're going to do is for each one of these points, for each of the VI, only store the argmax over all I over all j from 1 to n of the dot product of pj with VI. So we get a core set of size t, which is O of 1 over alpha to the d minus 1. So does that make sense? I mean, the perfect core set would be, the perfect core set, which wouldn't lose any information, would be, don't just take a net of the sphere, but take the entire sphere. This is it's an infinite number of points. And what we'll remember is, for every point on the sphere, I'll remember who has the largest dot product with that point. And I'll just remember that guy. Okay, because if you think about it, like if you think about the optimal solution to minimum enclosing ball, so I have a bunch of points. I'm trying to find the minimum enclosing ball. Okay, let me ask you, is this the minimum enclosing ball? Could that be the minimum? Let's say the black points are all there is. There are no other points besides the black points that I drew in this example. Could this red ball be the minimum enclosing ball?
Yes.
Wait, why do you say yes?
Oh wait.
So I guess maybe my question wasn't super clear, but I mean, forget about generalities. This specific set of black points, is this ball optimal or not?
No, it's too big.
No, it's not.
It's too big, right? And basically, I mean, any ball, the point is any ball which is optimal should have at least one of the black points on the boundary, right? Because if there are no black points on the boundary, I can just take the ball and shrink it around this. This is a ball around some center. That's the center, let's say. I can just consider balls around the same center that are smaller and smaller and shrink them until I can't shrink them anymore. And why can't I shrink it anymore? I can't shrink it anymore because I just hit a black point, right? So like, even for this particular center, the best ball around this particular center is probably the one that like touches, these black points that I'm now touching. I can't shrink it anymore because otherwise I would fail to include that black point. Okay. And then you could then say, okay, now look at the black point that is on the boundary, and look at the line segment from the origin to that black point, right? What is that? This is just some direction in the sphere. All I really care about is the direction. I don't really care about the length right now. So that's some direction in the sphere, right? So this point P is the argmax over all, let's say, points P prime in the point set. Let's call it P star. This is P star. P star is the argmax over all 1 less than or equal to j less than or equal to n of pj dot v, right? It is the points in our point set that has the largest projection onto that direction, because it's the points in our point set that defines the radius, and this is the direction of the radius. This is the direction that defines the radius. Does that make sense? So the point is, if I said that we're going to store, for all v in the sphere, we're going to store the argmax of pj.v, then that would be a perfect core set, because like whatever the true radius is in the optimal enclosing ball, that direction between the origin and the point on the boundary of that ball, that direction will be captured by this, and P star will be included as the argmax for that particular direction.
That seems equivalent to remembering or like keeping all the vertices of the convex hull of the points.
Right, except the problem is that it's not in, we don't know what the center should be, right?
Right, but I'm saying for the definition of the core set, at least. It seems like
you're saying it's take the convex hull of,
or like keep all the vertices of the convex hull of the P sub j.
Yeah, I'd have to think about that. I'm not convinced that that's right, just because convex hull is more of an L1 thing than L2, but than L2 balls.
Right. Or yeah, I'm sort of reminded by like the alternative formulation of the like Gaussian mean width, where it's like the difference, or I guess, okay, maybe we don't want to go too much into the tangent here, but.
Is it? Yeah, so I mean, we can come back to that, but this is what we're going to. So basically, the thing that would be perfect would be taking the argmax of the dot product with anyone in the sphere. The problem is that might not shrink our point set at all. Each one of our points might be the argmax for some particular direction. But at least this way, since we're only taking a net of the directions and not all the directions, we're basically promised that the number of points that we have to remember is at most the net size. Okay. So now the question is like, why is this a core set, and what alpha should we choose to make this a core set? So our goal is a core set with approximation ratio 1 plus epsilon. And the question now is like, what alpha do we need?
Or actually, sorry, these inner products are all like optimizing over P is like optimizing a linear program, right? So like the P's that you pick are exactly the P's which can be the optimal to some objective.
That's right.
So that seems like it would mean that the P sub j's you keep are exactly the vertices of the convex hull.
Yeah, that sounds reasonable, actually. That does sound reasonable.
Well, I guess certainly.
I think the one problem might be, though, I mean, what's the runtime to compute d-dimensional convex hull exactly? I think that might not be fast in high dimensions. But even so, I guess.
Oh yeah, it might not be an efficient way to compute it, but.
And even aside from efficiency, like, it might be that every one of the P's are. Oh, I see. Yeah, but I guess the point is, right. Yeah, maybe that what you're saying also makes sense. I have to think about that. Maybe the problem is only efficiency.
Okay.
So kind of what alpha do we need to choose to make sure that this is a core set? So here's the picture that I want to draw. So let's say that basically what I want to say is what I want. So let's say a weak core set. What I want is if I compute the MEB of the core set, then increasing it, the ball radius by at most 1 plus epsilon, let's say, covers all points. We already know that the radius of the MEB for the core set has to be smaller than or equal to the actual optimal radius, right? Because the P's that we're keeping in the core set are a subset of the original P's. So any ball that covers any ball that covers all the points has to cover the core set. So opt can only be smaller for the core set. And what I want to argue is that it's not too much smaller. That if you take the optimal ball for the core set and just increase it slightly, you do get a ball that covers all the points. Therefore, that's a way to get you a ball for the original data set, which is within 1 plus epsilon of the optimum. Okay. So let's say that there's some, we have the subset, and we take the minimum enclosing ball for the subset. Which, the reason that, if it's the minimum enclosing ball, there's some point, P prime is in the core set and is on the boundary of the minimum enclosing ball. And for ease of notation, I'm just going to assume that the center is 0, because otherwise I'll just translate the picture so that it is. And also, if I'm just going to assume that the norm of P prime is 1, because everything that I'm going to say from now on is relative to the center and to the scale, which is the norm of P prime. So I can just translate and scale the picture. Okay. So let's look at some other P. So okay, first of all, if all the original points are in this ball, great, then I haven't lost anything. Otherwise, maybe there's some point P that's outside the ball. Okay. And let's take the P that defines the sorry, let's take the P that defines the radius that's on the boundary of the optimal ball for the original point set. Okay, let's say take the P which is furthest away from the center. I guess that's really what I want to say. So that's, let's say, this P. If it's inside the ball, great, I'm done. If it's outside the ball, then I want to say something. So let's say that this direction is W. Okay. Or let's not say it's W, let's say it's V. I know because I have a net, I know that there's some other V prime which is in the net. So this angle here has to be at most alpha. Okay. So what do I know? I know that P was not included in the core set, but P prime was, and P prime has norm 1. Okay. So if P was not included in the core set, it must be because what did I want to say? So I think, do I have a... Yeah, I guess what I want to say. I just want to look at this dot product P dot V prime. Just give me a second. So P dot V prime, what do I know that equals? That equals the norm of P times the norm of V prime times the cosine of the angle between P and V prime. And I know that this thing is at most, it's at most the maximum dot product with V prime amongst the point set, right? Since P was not included in the core set, there must have been something else in the core set that had a larger dot product with V prime. And what can I say about that point's dot product with V prime? Well, that point is contained within this ball of radius 1. So that point's dot product with V prime had to have been at most 1. So this is at most 1. The norm of V prime is 1. These are L2 norms. So this all implies that the norm of P is at most 1 divided by the cosine of that angle. Let's just call that angle theta. And this is at most 1 over cosine of alpha. And what do I know about the cosine of alpha? When alpha is small, I know that the cosine of alpha is basically 1 minus theta of alpha squared. This is by Taylor expansion. So this is at most 1 plus big O, or 1 plus O of basically alpha squared. Right? And I want this to be 1 plus epsilon to argue that if I just increase the ball by 1 plus epsilon factor, it'll contain all the points in the original point set. So basically, I want this theta alpha squared term to be epsilon, which implies that alpha should be basically root epsilon. So that implies that my net, which has size theta of 1 over alpha to the d minus 1, is actually theta of 1 over epsilon to the d minus 1 over 2, as desired. And that's basically it. So are there any questions about this construction or the analysis of it?
Yeah, actually, so the initial dot products are computed with respect to the initial center of the ball is the origin. You
mean initially when you take dot products?
Like the V's. I guess. Yeah. Okay, I guess like.
So I think yeah. So I think I see what you're saying, which is basically,
like what if the
what if the center is not the origin, right? But everywhere, like let's say the center here was not the origin, but was some other some other point Q. Then fine, just instead of V, look at like V minus Q. Think of it as V minus Q and V prime minus Q. And
but I guess like, is there any requirement that the origin, like the P's need not be centered, right? The P's might be very far away from the origin.
That's true.
Right. Okay. So then what I said earlier about it just being the convex hull is not completely correct, right? It's like the vertices of the origin union with the P's.
The vertices of the
convex hull of the origin union all the piece of J's.
Oh.
Right, because there are instances where you need to, or you don't, or some particular piece of J might be on the convex hull of the P's, but you don't want to include it in this core set because it's like closer to the origin than all the other piece of J's.
I'm not sure right now.
Okay.
But most of what you're doing, you're still saying though that you should be able to reconstruct a core set via some convex hull computation, right?
Yeah.
It's just on one more point.
Yeah.
Okay. Yeah, I don't. The thing is, I don't know offhand. I mean, I do know that runtimes behave very poorly for convex hull in high dimension. I think it maybe is also like exponential in the dimension, but I don't remember the exact. I don't remember the exact runtime.
Okay.
Like, for example, is it something like n to the d or n to the d over 2 or something? Maybe it's better. I'm not sure. I'm not sure exactly. I'll have to look that up.
Okay.
So I think basically we're out of time. But any other questions before we move into final projects on Wednesday and beyond? Okay. So I hope you enjoyed the semester, and I will see you all Wednesday for projects.